So last week, if you'll recall, we started talking about MRI and the fact that MRI deals with active nuclei, which I've represented over here on the left. And what makes an active nucleus is the fact that it's imbalanced, right? It's got different number of protons and neutrons, and as a result, when you put it in some external magnetic field, it's off axis and it wobbles, and it wobbles at some speed, some frequency called the Larmor frequency around its long axis. So by way of example, if we put a patient into our 1.5 Tesla scanner, into that big external magnetic field, we zoom up here. So within that patient, all those protons, all those hydrogen nuclei are going to line up in one of two orientations, right? They're either going to be in an anti-parallel orientation or a parallel orientation. And if we look at that sample as a whole, there's some tiny excess that line up in the anti-parallel orientation. And so if you sum that all together, you get some net magnetization in this longitudinal direction, which is this yellow arrow here. And we said, okay, well, that's very well and good. We've generated some net magnetization within our patient, within our sample. But this alone is not of any use to us because we can't measure it directly. We can't measure it directly because it's in the plane of this much larger magnetic field. Okay, and so we talked about how in order for us to be able to measure anything, it needs to be outside of the plane of that larger field. It needs to be perpendicular. So we said, okay, well, if we can generate something that's perpendicular, that looks like this, we could measure signal. And we talked about the way that we could do that is to use some external energy source, another field applied in the perpendicular direction, which we're going to call our RF pulse, right? And you'll recall that, we said we could use that perpendicular field to, raise this whole system to a higher energy state and get to this point, kind of like over here on top right. We start from bottom with increasing energy levels here. We've put the patient in the scanner. We've generated our longitudinal magnetization. As we add more energy in the form of the RF pulse, now we get up to here. And then the last thing we touched on is, it's not sufficient to just turn on another field in this direction, because to get to that higher energy state, to get this transverse magnetization, we'd have to cook the patient. And so rather than cook the patient, we exploit this property of resonance, where we turn on this field, but we turn it on and we alternate it at some frequency. And as long as this frequency matches the frequency of the protons that we're interested in within this patient, there's going to be very efficient energy transfer, right? And so, at B with some field strength B0 over here, we said that, B0 is proportional to frequency of spins. So if this is B0, all the spins that are sitting in B0 are going to have some frequency sub-zero, like this. And as long as we match our RF pulse to that frequency, then we get efficient energy transfer, and we generate this vector. Okay. We also said that the other thing that's happening is as this vector is going from being in the longitudinal axis, and we're putting it in the transverse axis, we're also taking all of those spins that were out of phase with one another, and we're putting them in phase, which is down here at the bottom. And so your phase diagram would look something like this, where now they're all clustered together and you have some measurable signal. So hopefully that looks pretty familiar to everyone. Pretty basic concepts, but just to review. Different way of saying the same thing. So when we turn our RF pulse on, which is here, okay, we're taking our longitudinal magnetization and we're standing it up. Okay, and if you were to plot what's happening to our yellow arrow and our orange arrow. I'm going to say orange, you might say red, but I'm colorblind. If we plot what's happening to this over time, like on this graph here, this is just the magnitude, okay, of the magnetization vector. How big is the vector? And this is time on the x-axis. So over time, what's happening to the size of our yellow arrow? Well, it's getting smaller all the way down until you don't have any longitudinal magnetization, okay? And what's happening with our orange arrow? Well, it's growing up until a maximum amount that's equal to the original value of our longitudinal magnetization, and this is our transverse magnetization right here in the orange. Okay, this is just a graphical representation of what's happening here. When we apply our RF pulse, we turn it on here at this time, and we watch transverse grow and longitudinal decay down to zero. And this is just a reminder here that as we're doing this, and as this vector is getting smaller and this vector is growing larger, the other thing that's happening is that all of these spins that were dephased before, when you apply that RF pulse, now they're in phase. Okay, and so that's just all summarized here. When we turn on the RF, our longitudinal magnetization decreases to zero. That's the yellow. Transverse magnetization increases. Okay, that's the orange. And our phase becomes coherent, which just means that everything is in phase. Okay, so what happens when we turn the RF pulse off? So, just to take a step back, when we're acquiring these images, we're turning this RF pulse on and we're turning it off countless times. Okay, so our turning the RF pulse on is our way of, putting energy into the system. When we turn it off, what's going to happen? Well, it's pretty basic. Energy is going to, leave the system, and it's going to return back to where it was. Okay, so over here, this half of the graph, this is what we just talked about. We turn on RF here at this time. We watch our transverse magnetization get larger and our longitudinal go down to zero. And everything is in phase at this point. When we turn our RF pulse off, okay, we're not putting energy into the system anymore, what happens? Okay, transverse magnetization will slowly go back down to zero as things go from in phase to out of phase, and longitudinal will slowly regrow. Now what you'll notice here is that these are happening at different speeds. Okay, transverse is going to go back down to zero, longitudinal is going to go back up to its max. Okay, but they don't happen at the same rate. And it turns out that different tissues will do this at different rates. And what MRI is all about is, turning this RF pulse on, getting them to this higher energy state, then turning it off and just watching what happens. That's basically all we're doing over and over and over and over again. Putting energy into the system, standing things up, and then taking energy out of the system, watching them fall back down, and comparing the rate at which they fall back down. Okay, the rate at which this decays, the rate at which this recovers. Okay, that's the basic premise of what we're doing here. So this is just summarizing exactly what I just said. Another way to think about this is, if you have a bowling ball and a piece of paper, and I'm not talking about, in a vacuum or anything, just, here on Earth, if you put energy into the system and you raised the bowling ball and the piece of paper up to the same height and you dropped them, even if you didn't know that you were dealing with a bowling ball and a piece of paper, you didn't know what they looked like, you didn't know where they were. If all you had to go on was, their speed, and their path plotted on a graph over time, I bet we could all pick out which one is the bowling ball and which one is the piece of paper. Okay, that's the concept of what we're doing here. We're putting energy into the system, we're taking it away, and then we're seeing what happens. And we're using the difference in how different tissues respond and how they return to baseline as a basis for the contrast in our image. So this is the same idea here. just, again, I'm going to hammer this home in as many ways as I can, just shown a different way. This is our higher energy system with our transverse magnetization and our RF pulse on. That's this time point here, right at the beginning. When we turn off the RF pulse and let the system go back to what we had initially with just longitudinal magnetization, that lower energy state, this is what's happening in graphical form, okay? This transverse magnetization is going to decay back down to 0, and our longitudinal magnetization is going to recover back to its original value. This is relaxation. It's relaxing in a longitudinal and a transverse direction. And then this is what's happening from a phase perspective. Everything's starting off in phase and it's becoming out of phase. Okay. So over here, I've said the same thing with the RF pulse off. The system's going to return to normal. Both of these curves represent energy loss, right? Returning to a lower energy state. This is size of the vector on the y-axis. This is time. Energy loss is going to occur at different rates, and that's because there's two different mechanisms that are governing how the system is losing energy. Okay, spin lattice or spin and spin lattice, and we're going to talk about that in a second. Okay, so let's look at what happens with the transverse magnetization a little bit more closely. This is the same as what we've shown on the last several graphs, but we're just kind of separating it out by itself. So when we talk about relaxation, relaxation is just describing the release of energy over time. Okay. After you turn that RF pulse off, how does the system get rid of energy? It doesn't just disappear. The system has to get rid of energy through some mechanism. Okay. Conservation of energy and all of that. So with transverse magnetization, you may hear it called, transverse magnetization relaxation or decay, means the same thing. This is an exponential curve, so it relaxes or it decays exponentially over time. And the mechanism that it decays by is through spin-spin interactions. Okay, what the hell are spin-spin interactions? This is interactions between two protons, two hydrogen nuclei, two of our spins, okay, interacting with each other, exchanging energy, and it's those interactions, it's through those interactions, through those protons bumping into each other, imparting some energy to each other, that the whole system slowly returns to a more, chaotic, lower energy state. Okay. And this is where T2 comes in. T2 is basically the time at which the system has decayed to 37% of the original. Okay. So doesn't matter if it's bone, doesn't matter if it's muscle, doesn't matter if it's water, doesn't matter what it is. The T2 of that tissue is defined by the time at which, there's 37% of the original transverse magnetization. Okay. So another way to look at this is, if something is decaying faster, if something is getting rid of its energy faster, right, its curve is going to look more like this. It's going to be shifted to the left. You're going to have a shorter T2. Okay. If the system hangs on to its energy longer, if it takes longer to return to baseline, it's going to decay slower, and you're going to have a longer T2. This is kind of the key right here. So just to sum up, transverse magnetization decays exponentially. It's doing this through spin-spin interactions, which are interactions between spins, between our nuclei. T2 is what time is there 37% of the original transverse magnetization left. And then if I said, something is decaying faster, what's going to happen to the T2? Well, it's going to be shorter. If something is decaying slower, well, then your T2 is going to be longer. Okay. So a little bit more on spin-spin interactions. We said it's the exchange of energy between nuclei and other nuclei. So one example would be water. Okay, so the blue is the curve of water. Okay, in water, nuclei are more free, right? It's free flowing, free moving. There's less probability of those water molecules, those water nuclei acting with each other, right? So, like we said before, okay, if there's less probability of those spin-spin interactions occurring, your decay is going to be slower. It's going to take longer time for the system to get rid of energy through that mechanism. And that's this blue slope here, okay? And as a result, the T2 of water, if we figure out, okay, at what time is there only 37% left, T2 of water is out here. Compare that to muscle, right? Muscle is not free flowing, it's not a liquid. Okay, it's a tissue, it's complex biological tissue, and as a result, there is a greater probability of spins within the muscle undergoing those spin-spin interactions, exchanging energy, which means that the system as a whole is going to get down to its baseline, down to zero, a lot faster. So that's this red curve here. And we said that if you have faster decay, right, then your T2 is going to be shorter. It's going to take less time for you to get down to that baseline. So if we compare the T2 of muscle and the T2 of water, the T2 of water is going to be longer. Okay. Now notice, these curves are different, and so it would be nice if we had a way to exploit this difference, right? Because this is what's going to give us our contrast, is this difference in the rate at which water, relaxes and muscle relaxes. Okay, so that was transverse magnetization. What's happening with our longitudinal magnetization? Okay, so same concept over here on the y-axis. This is just how much magnetization do we have? How big is that yellow arrow? And this is time on the x-axis. And as the system is going back to a lower energy state, as we turn the RF pulse off, here at time 0, and now we watch what happens. As the system is giving off energy, you're going to have regrowth of your longitudinal magnetization. Okay, that's again relaxation. It's energy losing the system. You might also hear that called recovery, right? Because this is kind of recovering to what it was originally. Again, it means the same thing. Whereas before with transverse magnetization, this was through these spin-spin interactions. With longitudinal relaxation, this occurs via spin lattice interactions. These are different. Okay, this is interactions between the spins that we're interested in and all of the other stuff that's in the body. Okay, and this curve is described by T1. So transverse magnetization was described by T2. Longitudinal magnetization is described by T1. And we define this as the time at which there's 63% of the maximum regrowth. Okay, how long does it take for us to go from 0 to 63% of our maximum longitudinal magnetization? Okay, whatever that time is, we're going to call that T1. So we can kind of prove to ourselves that, okay, well, if something is recovering faster, if it's able to hand off energy faster through these spin lattice interactions, well, if it's doing this faster, it's going to have a shorter T1, right? Because it's going to get to this point, this level, quicker. So your time is going to be shorter. And on the other hand, if it's not so great at getting rid of energy through these spin lattice interactions, you're going to have a smaller slope to your curve. It's going to take longer for it to reach, its maximum, and your T1 is going to be longer. It's going to take more time to get to 63%. So this is what we just talked about. Same idea, right? We got muscle, we got water. So just like there was a difference with the transverse magnetization and how fast that decayed, there's a difference on the longitudinal side with how quickly these things recover. So muscle, right? Well, we can do water first. So water nuclei are, again, they're more free. they're moving around, there's more Brownian motion, etc. So there's less probability of these water molecules interacting with the lattice. Okay, and as a result, it takes longer for them uh, to reach the max. It takes longer for them to reach 63%. Therefore, the T1 is longer. Muscle, on the other hand, okay, it's complex biological tissue, and because of that, it's easier for those spins to hand off energy to other spins in the lattice, to the rest of the lattice. Lattice, think of it just kind of as a, like the superstructure. And so the more organized things are, the easier it's going to be to hand off energy in that way. And that's why this curve, it gets to 63% shorter, right? So your T1 is going to be shorter. And again, we've got a difference between curves, right? The muscle is going to recover at one rate, water is going to recover at some lesser rate. When we add contrast, right? If we add gadolinium to a patient, what's that doing? Well, it basically is increasing the probability of these spin lattice interactions. It's that's why we say contrast is T1 shortening, because essentially what you're doing is you're making a curve that looks like water. You're making it look more like muscles curve. Okay, so that's the basis for contrast here in our images. It's exploiting the different rates that different tissues will recover after you turn your RF pulse off. Time to echo. What is this? TE. May or may not have heard of this. So this is a fancy word or fancy term for, basically it's just when we choose to measure our signal. Okay. So again, we've set this up the same way. On the y-axis, we have our transverse magnetization. The x-axis is time. So we're looking at what is happening to that transverse magnetization over time. On the very far left, we've turned our RF pulse off. So we're going to watch these things decay. Now, and at any point along this time, we can decide to sample the signal. Okay, because this is transverse magnetization, we can actually measure this signal. This curve is a representation of how much signal we have over time. Okay, hopefully that makes sense. So if we can choose our time that we're going to measure this signal, which is TE, right? It's just time to echo, time at which we measure the signal. Where do we want to put that? Where do we want to measure in order to get the most contrast? Well, based on the way I've drawn these curves, it looks like, TE2 is going to be better, right? Because there's a greater difference between your water and your muscle compared to TE1, where there's less of a difference. You might still be able to tell them apart, okay? But maybe not as easily as over here. And remember, contrast is the ability to discriminate between two things that are right next to each other. So this is your difference in contrast right here. T2 contrast, that is. Okay, so again, example, with the shorter TE, TE1, there's less difference between the curves, so you have less T2 contrast. Okay, TE2, right here, right? There's more difference between these curves, between water and muscle. So the signal that you measure is going to reflect more contrast based on their, T2 properties. Key concept here is a longer TE is going to maximize T2 contrast, generally speaking. Okay. Longer TE, as you wait longer, this difference becomes greater on average. Okay. So that's a pretty core concept. Okay, so far we've said, okay, all this stuff in the sample gets rid of energy at different rates, right? It's described by unique T1 and T2. Okay, all of these things in our patient are getting rid of energy after we turn off the RF pulse. They're doing it at different rates, and that means that everything in the patient is going to have a unique T1 and then a unique T2. All the different tissues are going to have unique curves, unique rates at which they get rid of stuff, right? T1, how fast does our longitudinal magnetization recover? It's this on the left. How fast does it do that through the spin lattice interactions? T2 is how fast does our sample dephase? How fast does the transverse magnetization, how fast does our signal decay? And that's through the spin-spin interactions. Okay. And like we just said, image contrast comes from exploiting the difference in how quickly these things relax. Okay. We used the example of muscle and water. And we talked about how we can manipulate TE, basically how we can choose, depending on when we decide to measure the signal, we can increase or decrease the contribution of differences in T2 to our signal. This is the concept of T2 weighting. If you want a more T2 weighted signal, right, you're going to choose the longer TE because that's going to maximize the differences. Okay. So far, I hope that this makes fairly straightforward sense as far as how, we get information about T2, differences in T2 into our signal, which you can see right here. The next question is, okay, so we talked about T2 and how, how that contributes to our final signal. What about T1? So if you remember, the issue with T1 is that this axis over here, this recovery, this is longitudinal magnetization. And remember, the whole point of getting stuff in the transverse plane was that we can't measure this directly. So all of this you can't measure directly. We're just stuck with curves that look like this. So what do we do about T1? Okay. A lot going on here, but it's actually really straightforward. So this at the top is what we've seen before. Okay. We have how big our magnetization is on the y-axis, right? This is just how big is the arrow, and on the x-axis is time. Okay. At time 0, we've turned off our RF pulse and we're watching what happens. Transverse is going down to 0, longitudinal is recovering. Okay, that's everything that we just discussed. And then once the longitudinal has recovered all the way up to its original, let's say you hit it with another RF pulse, which is this line here. What's going to happen? Well, you're just going to repeat the same thing, right? Transverse is going to go back down to 0. You're going to knock the longitudinal down with the RF pulse, and then you're going to watch it recover. Okay. The time in between your original RF pulse, which was over here at 0, and this next RF pulse is something we're going to call TR. Okay. It's time to repetition. It's the time in between repetitions of the RF pulse. How often are you applying your RF pulse? Okay. So this is a scenario up on the top where we've allowed enough time for the longitudinal magnetization to recover all the way up to 100% of what it was before we knocked it down. Okay. So what about a scenario where instead of giving it all of that time, we knock it down early? We apply this RF pulse earlier. Well, it's going to look something like this down here. Okay. We apply our initial RF pulse and we watch what happens. Transverse decays, longitudinal starts to recover, but before it can recover completely, we hit it with an RF pulse again. Okay, so now what's going to happen? Well, it's going to go back down to 0, and then we're going to watch it recover again. And the transverse is going to go back down to 0. Okay, but you'll notice something here. Because we've knocked it down early, right, we have less, at this point right here, we have less signal to work with. Okay, and so the transverse magnetization is also not starting from the same spot. Okay, initially it was starting from up here. Now it's starting from down here. Okay, so this curve is going to look a little bit different. And so we watch this go back down to 0, we watch this recover, but again, before this goes any further, we hit it with an RF pulse again, and we watch the same thing. Okay, so it's by manipulating our TR time, how often we're applying that RF pulse, okay, that we can make changes in these curves. So let's look at some examples here. So here we've got muscle and water. Okay, this is what we've shown before. We have our RF pulse, and we turn it on and we turn it off, and then we watch it recover over time at some TR, some time to repetition. And this is what our standard transverse, decay looks like. So these are things that we talked about initially, right? This should look really familiar. And let's say that, based off of this, we pick a time to echo, a time to measure our signal right here to maximize that contrast. Okay, so this and this is a scenario where we've given ourselves all the time to recover back up to full. Okay, now let's do just what we did over here, but using this practical example. So now we have our curve here, but instead of allowing longitudinal magnetization time to recover all the way to max, we've applied our RF pulse early. Okay, what is that going to do to our transverse magnetization curve? This difference between the muscle and the water at this time is reflected in where these curves start from, if you can see that. Muscle is starting from up higher here. Okay, you have more, muscle has recovered more in this period of time because of this, it recovers more through those spin lattice interactions than water does, right? And so because it's recovered more, when you knock it down, you're starting from a higher place. You have more signal to work with. And that's why muscle starts from up here. Water hasn't recovered as much. Okay, so when you apply your RF pulse again and you knock it down, it's starting from a lower level. When you knock that longitudinal magnetization down, let's go back to something where we have, okay. When you knock this guy, I mean, you're knocking it up in this image, but you can imagine when you're knocking this guy down so that he's 0, the amount of transverse magnetization that you have depends on how much longitudinal you had to start with. Okay. So if this is small, then when you knock it down, you're also only going to have a smaller amount of transverse magnetization. If this is bigger to begin with, then you're going to have more transverse magnetization. Okay. How big your transverse is when you apply your RF pulse depends on how much longitudinal you had to start with. This goes way back to the concept that we talked about, in the first lecture, where if you have a difference between a 1.5 Tesla magnet and a 3 Tesla magnet, right? With a 1.5, this vector is going to be, a certain size. With a 3 Tesla magnet, a stronger external field, your net magnetization vector is going to be bigger, which means you're going to have more signal to work with when you knock it into the transverse plane. That's one of the advantages of a 3 Tesla, is that it gives you more signal to work with. And what we're saying over here is that if you apply your RF pulse again without waiting for these both to recover all the way, then depending on how far they've gotten before you apply this again is going to determine where they start on their transverse kind of decay curve. And so to sum up, what's happened here is by adjusting how often we're applying the RF pulse, we've taken this difference in their longitudinal relaxation properties between muscle and water. We've taken the difference in that relaxation and we've sort of encoded that difference in our transverse curve. Remember, this is the thing that we can measure. We can't measure this directly. This is longitudinal. This is in the plane of the magnet. This is what we can measure. So here, this was without any contribution from what's going on up here, right? Because they're both starting off the same part. But once you start messing with how frequently you're applying your RF pulse, now you start to get some contribution from the difference here. So that what we actually end up with are curves that have a combination of both information about difference in the the rates of longitudinal relaxation, difference in T1, and the difference in T2, right? So this is a combination of information from here and from here. So that's how we're getting our T1 and our T2 contrast. Okay, this is the same thing, just made to look even more intimidating, but it's the same thing. Okay, so we have the same axes over here. Okay, this is our longitudinal, and this is our transverse. This is how big is the arrow getting, and this is time. So we've set it up the same way. We're watching our longitudinal recover. We're watching our transverse decay over time. And what I've done here is I've basically given us examples at 3 different TRs, okay? Basically showing the difference between what happens at a short TR versus like a mid TR and a long TR. So you'll notice that if we were to allow enough time for everything to get back to our starting point and then we knocked it down, that's this over here, right? They're starting from 100%. Your transverse magnetization is starting from its maximum potential, and this is the curve that we've talked about, several times before now. This is what would happen. Okay, and then we said that if you shortened that, and instead of waiting all the way out until your longitudinal vector has recovered fully, instead of that, if you time your RF pulse, your next one, earlier at one of these TR times, you're going to end up with curves that look like this, right? And you can see that, okay, if we have a really short TR, right, we hit them with an RF pulse, we knock them down, we watch the longitudinal start to get back up. If we hit it, knock it back down again pretty quickly, there's a pretty big difference between muscle and water here, right? And that pretty big difference between muscle and water in the way that they are releasing energy through those spin lattice interactions, right? T1, difference between their T1, properties is encoded in the transverse magnetization curve, right? So if we measure our signal here at TE, there's no difference between water and muscle, right? This is why, trying to look at, trying to discriminate between, like an abscess and surrounding tissue on a T1 weighted image, which is a short TR, is really hard because they look the same. You have no contrast here, right? Conversely, if we take a longer TR, we allow more time for this longitudinal magnetization to recover. When we apply our RF pulse again at this time point, most of the magnetization is recovered, which means that we're starting higher up. We have, we knock this down, and if we knock it down from here, that means the transverse magnetization is going to be starting from up here. And you'll notice there's less of a difference between muscle and water at this time point, right? They've kind of recovered to roughly about the same level. And that's reflected down here, as these guys are starting from, pretty close to the same point. Well, this curve looks kind of like this curve over here. Remember, this curve was without any contribution from longitudinal. So this is kind of more if you wanted to maximize your T2 contrast, right? The amount of contrast between the T1, between the longitudinal relaxation, which is this little yellow bar here, is shown here. It's not making as much of a contribution to these curves. Okay, so this with a long TR actually looks mainly like this. Okay, where you're maximizing your T2. So you can see one of the trends I want to point out here is the fact that with a short TR, you're really maximizing the amount of information about differences in T1 that show up in your final signal curves. Okay, because again, this is what we can measure. We can't measure this stuff up here. This is what we can measure. So which of these curves is most affected, by changing the TR? Well, it's this one. So at short TR, we have the greatest amount of T1 contrast embedded in our signal. At longer TRs, this is going to look more like our T2 curve. Okay. That's core. That's okay. Just going to say it again. The relationship here, this is what we just looked at. Okay. If we want to encode more T1 contrast in our image, we use a shorter TR. Okay. That's what we just looked at. The trade-off here is that if we make our TR shorter, we have weaker signal overall. So with a shorter TR, look where we're starting from. We're starting from down here. Both of these are starting lower than they would have if we, gave them all the time to recover. Okay, with a short TR. So we have less signal to work with. When we measure signal at TE, that is going to be lower. Okay, so as you shorten this TR, you have less signal to work with. If you're trying to maximize your T1 contrast, you're eventually going to run into a point where, there's a trade-off now. The more T1 contrast you want to put into your image, the less signal you're going to have to work with. Okay, and look, over here, these curves are higher up, at TE where you're measuring, there's more signal here because you've waited longer for longitudinal to recover before knocking it down. Okay, and then with T2, same deal. So if we want to put more T2 contrast in our image, what are we going to do? Well, we talked about that before. We're going to use a longer T2. We're going to measure here and not here. But it's the same deal. What's happening with our signal curve? It's getting smaller over time. The longer you wait, the less signal you're going to have to work with. Okay, so the trade-off again with T2 is that if you make your TE longer to maximize your T2 contrast, right? You're waiting to, to make this difference as big as possible. The longer you wait, the less, the smaller these curves are, the less signal you've got to work with. Okay, so these relationships are important. This is just another way of representing what we just said. Okay, so what did we say short TR was? If we make our TR short, what are we doing? Well, we're weighting our signal towards T1, right? That was this. That was this right here. Short TR, more T1 contrast in our final signal. Okay, so that's short TR. And if we want to make a T1 weighted image, well, then we want to have a lot of T1, and we want to, minimize the amount of T2 contrast. So we'd make our TE short, right? We want all of this showing up, and we don't really want this difference showing up, so we might measure our TE here, where there's less information about the difference in T2 being imparted. Okay, so T1 is going to take, if you have a dial on your MRI scanner for TE and TR, you're going to set your TR to be short and you're going to set your TE to be short, and that's going to give you a T1 weighted image. And then T2 is the opposite. It's long and long. If you want to minimize the amount of T1 contrast, you're going to make that TR really long, right? We saw here there was very little T1 contrast being imparted into our signal curves at a long TR. And then a long TE, you want to wait to allow enough contrast between those decay curves. So if you want a T2 weighted image, you're going to set your TR long and your TE long. Okay, this scenario does not exist. So what is this? Short TE, long TR. What's that going to look like? So this is proton density. Basically, short TE, long TR. Long TR, we just looked at, you're minimizing your T1 contrast. Short TE, we also just kind of looked at, that's where you're minimizing your T2 contrast. Okay, right here and right here. So if you're minimizing the contribution of T1 and T2, if you're basically saying, I don't care about the difference in the way that these different tissues relax, what are you left with? What's the only thing, where's your signal coming from? And in this scenario, it just simply depends on how many spins do you have. What's the density of spins? Things that are more dense, things that have more spins, are going to have more signal and are going to be on a higher curve. That's your proton density weighted image. Proton density depends on basically just the density of spins, minimizing the T1 and the T2 contributions to the signal, And as a result, it's going to be higher, right? You're starting up here on this curve. So you're going to have more signal to work with than your T1 and your T2 images. And because you have more signal, that means that your proton density images are going to have the best signal to noise ratio, which we'll talk about later. So that's proton density. That's what that is. You're basically just adjusting your settings, your TR and your TE, minimizing the contributions of T1 and T2, and you're just focused on how much signal is related to the density at a particular point. Okay. So now our final chart looks like this. Last thing I'm going to touch on here, magnetic susceptibility. Okay, remember back, this is our T2 curve again. Okay, this is not something totally different. This is our T2. Okay, we have transverse magnetization over here on the y-axis, and we have time. What's happening? We turn our RF pulse on and off, and we watch our transverse magnetization decay back down to nothing. Okay. The point of magnetic susceptibility is that up until now, we've talked about, this relaxation. It's been idealized. It's assumed that the magnetic field that we're putting our patient in is completely homogeneous. Okay, and the fact is that it's not in reality. So T2 is idealized. This is like what we would expect if our system was perfect. Okay, systems aren't perfect. They're, inhomogeneous. And so the actual curve is in red. And that's something that we call T2 star. Okay, this is like real, this is idealized. This is real. Okay, so why is T2 star, why does the curve look like this? Why is this decaying faster than T2? The reason is that, in reality, your field is not homogeneous. There's little ripples in your magnetic field. And those little ripples are going to have some local field strength that is greater or lesser than kind of your idealized homogeneous field. And if they have greater or lesser local fields, that means that through that Larmor equation that we talked about, if the local field is stronger, they're going to also have a slightly greater frequency as well. Okay. If they have a slightly greater frequency, well, they're going to get out of phase faster because they're moving faster than in an idealized state. And that's why this curve decays faster than your idealized, because there's things in the magnetic field that are causing your signal to decay faster than you would have predicted because your system's not perfect. So that's all that I have for this morning. I basically wanted to just take time and really hit this in as many ways as I can, because this is the basis for everything that comes next. This is the basis for contrast between tissues. Okay, so the next talk will be about spatial localization and kind of how we start encoding this signal so that we can figure out where the hell it's coming from. So.